Section 2.2, organizing quantitative data. A blank is constructed by drawing rectangles for each class of data. The height of each rectangle is the frequency or relative frequency of the class. The width of each rectangle is the blank, and the rectangles blank each other. Okay? So here, this is now a histogram. Histogram. So the width is the same, and here the rectangles touch each other. There's no space between them. There's no space between them. So with a bar graph, right, we had space between them. The width had to be the same, right? The height was the frequency or relative frequency. It's all the same. The difference is they touch each other, okay? So also with bar graphs, we were doing qualitative data. With histograms, we were doing quantitative data. So example 1, constructing a frequency and relative frequency distributions for discrete data. This is the number of arrivals at Wendy's. They have 40 randomly selected 15-minute intervals during lunch. So, for example, during one 15-minute interval, 7 customers arrived during lunch. So those are your different values: 752, 62, 66, 752, 66159, right? So here, during a 15-minute interval, only one person pulled up to Wendy's during that time. Here, 11 people came through in 15 minutes. Okay? So we're going to tally these up. Right? We're going to take all this data and tally it up over here and get these numbers. All right? And once we do that, then we can get the relative frequencies over here. So then we can put these things, this is a histogram. Notice the bars touch, right? So then there's your 1, here's your 1 bar, here's your 2 bar, your 3 bar, your 4 bar, 5. So for 6 cars pulling up at Wendy's out of those 40 times, it looks like that's what? 11 of them. So if we go over here to 6 and look at the frequency, then there it is, 11 right there. All right? And the one on the left is frequency. The one on the right is relative frequency. Blank are categories into which data are grouped. When a data set consists of a large number of different blank data values, or when a data set consists of blank data, we create blank by using intervals of numbers. That's a lot of blanks. So what are categories into which data are grouped? We're going to call those classes. Classes. So classes are categories into which data are grouped. When a data set consists of a large number of different discrete, right? 2 cars, 3 cars, 4 cars, not 4.5 cars, right? 2 discrete. Okay. Data values, so large number of different discrete data values, are when the data consists of continuous data, right? We create classes by using intervals of numbers. So either a large number of different discrete values or continuous data, we use classes by using intervals of numbers. So, what is the smallest value within a class? The smallest value within the class is the lower class limit. Now, it says the smallest value within a class. It doesn't say the smallest actual data point, but it's the smallest value that you will allow a data point to be in that class. All right? So then the largest value within the class is the upper class limit. Again, it doesn't have to be an actual data point, but it is the largest value that a data point can be and still fall within that class. Blank is the difference between consecutive lower class limits. Okay? The class width. Notice what it says. The class width is not the upper minus the lower. What is it? It's the difference between two consecutive lower class limits. We are going to figure this out. You're going to have problems where you do this. So you need to know it is two consecutive lower class limits, not upper minus lower. In a table, if the first class has no lower limit or the last class has no upper limit, then the table is what we call open-ended. So we're going to look at an example when we flip the page over here, but before we do that, let me just give you some general guidelines for determining the lower class limit of the first class and the class width. Choosing the lower class limit of the first class. Choose the smallest observation in the data set or a convenient number slightly lower than that. You don't want to go above it, right? Because then that data point wouldn't fall anywhere. So, for example, in Table 12, the smallest observation is 8.28, and that's what we're going to look at in just a second. A convenient lower class limit would then be 8. That's a little bit smaller than that. Determining the class width. Decide on the number of classes that you want. So if you may want 5 or 10 or 20 or 30 or 40. Generally, though, there should be between 5 and 20 classes. The smaller the data set, the fewer classes you should have. For example, in Table 12, we might choose 12 classes. Let me go and flip the page over here. And so in Table 12, the smallest value is 8.28. And then we have, 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5, 6, 7, 8. We got 40 data elements, so 12 classes with 40. Okay. You might could even say, well, I don't want to pick that many, and that's okay too. The class width is the largest data value minus the smallest data value divided by the number of classes. And then you round this value up. All right, so we went lower than the lowest value. Now we're going to round this number up. So in Table 12, 19.43 is the largest, 8.28 is the smallest, and we want 12. So then 0.929, we round that up to 1. And because that's an easy number to work with. It's a whole lot easier to do that than it is to go, let's start at 8.28 and add 0.929. No. And by using 1, we can go 8 to 8.99, and 9 to 9.99, and 10 to 10.99. And that makes it really easy when you start counting the values, right? If it's 10 point something, it goes in the tens. If it's 12 point something, it goes with 12. If you had it 0.929 and it was 8.963, well, you'd have to say, well, what is that in the 8 point to 8.9, or is that the 8 point? You'd be confused. And I know you didn't know what I just said because I didn't know what I just said. I was trying to sound confused. Okay? So if it's 1 apart, if it's 8 point something, it goes in the 8s. If it's 15 point something, it goes in the 15s. So that's what's beneficial here about using 1. So let's look over at Table 12. Table 13 is where we took Table 12 after we decided, hey, 8s, 9s, 10s, 11s, 12s. After we decided that's what we needed to do. Then we tallied them up. We got 2 in the 8s, 2 in the 9s, 4 in the 10s, 1 in the 11s, 6 in the 12s, 13 in the 13s. And then we got the relative frequency where we did 2 out of 40, got 0.05, 4 out of 40.1, 6 out of 40.15, right? 13 out of 40.325, so on and so forth. And then we have the 2 histograms down here. One is frequency, one is relative frequency. But depending on how we scale it, right? If we scale our relative frequency to match the height of its corresponding frequency, then our 2 histograms look identical. And all I mean is, if this is your line for 12 right here, just make this whatever corresponds to 12, which in this case is 0.3. And then it'll work out nice and neat. As far as those 2 things looking the same if you did them separately. So a blank is another way to represent quantitative data graphically, sometimes simply called a blank. So it's going to be technically and properly called a stem and leaf plot. And there it goes, taking that away. So let's got to do this. Sometimes it's simply just called a stem plot. Stem and leaf plot, sometimes simply called a stem plot. Digits to the left of the rightmost digit, right? Digits to the left of the rightmost digit create or form the stem. Each rightmost digit forms a leaf, hence stem and leaf plot. For example, the data value of 147 would have 14 as the stem. Here's the rightmost digit, and what's to the left of it? 14. That's where the 14 comes in right there. And then the 7 is going to be called the leaf. The leaf. So table 14 has the average percentage of persons living in poverty in 2012-2013. And it has the 50 states listed. So the first thing we do is say, okay, what's my rightmost digit? Well, it's the 10th, right? That's the 10th percent. 10th, T-E-N-T-H, right? It's the decimal, first decimal. So then everything to the left of the decimal is going to be my stem. So we have all the way down. The smallest one is in the 8%, and the largest one is in the 22%. So then we need our stems to go from 8 to 22. And then where did I get the 6 from right here? From 8.6 right here. 9.6 is this one. That one goes right there. And then I start with the 10s. 10.5, 10.8, 10.5, 10.1, 10.6, right? So I got 5, 8, 5, 1, 2, 6. Skipped a 2 in there somewhere. So, but that's what's going on there, all right? That's what's going on there. Set up your stems, then come back and add your leaves in. Add a leaf, each one that you get to. So what I would really do is come down here and say, okay, for the 16, I would put a 4. And then for the 10, I put a 5. And then for the 19, I put a 6. And then 18, I put a 6. And then 15, I put a 4. And then 11, I put a 2. And 10, I put an 8. And then you have these listed, and then what you do is you come back, you have all these listed, then you put them in order. You put them in order. From smallest to biggest. Put them in order from smallest to biggest. That's how you create a stem plot or a stem and leaf plot. So sometimes the data appear to be bunched, and so to resolve this issue, we can use something called split stems. Split stems. So here you have some, in table 15, you have some data. If you do a stem plot, right, it only goes from in the teens up to the 40s. So you have 1, 1, 2, 3, 3, 5, 5, 6, 7, 7, 7, 8, 8, 8, 8, 8, 9, 9 for ones. Holy cow. It's all bunched together. 2s, 3s, right there. 1 and 2 have way too many for just one, makes it tough. The one, this legend is here, 1 with a line and 1 represents 11. So then this number with this number represents 23. Okay? This number with this number represents 37. That's all the legend or the key there is telling us. What you can do is split the stems here, but you got to split them equal. So 0, 1, 2, 3, 4 is the first part, and then 5, 6, 7, 8, 9 is the second part. For each one. Same thing for 2. 2 and then 0, 1, 2, 3, 4, 2 and then 5, 6, 7, 8, 9. So plotting each observation horizontally in increasing order and placing a dot above the observation each time it is observed is called a dot plot. And here's an example of a dot plot for the Wendy's customers coming at lunch. And how many times each one of those things occurred over a 15-minute span? Or how many cars came, I should say. In that randomly selected 15-minute time during lunch. So that is a dot plot. Now notice, I want you to notice something. The first dot's all on the same level. The next dot's all on the same level. The next dot's all on the same level. You know, you don't want to have a dot plot where it looks like this. This one, and then this one, and then this one, and then this one, and then a big one again. And then this one's little and little and little. Right? You don't want that. If you have 3 dots, you want dot, 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 and you want the same thing over here. You want the same thing there, so that way it's all the same height right there. So it kind of reminds you of a bar graph, right? Kind of reminds you of that. So let me go ahead and get rid of this here. If the value of a variable is measured at different points in time, the data is referred to as what? Time series data. Time series data. And a blank is obtained by plotting the time in which a variable is measured on the horizontal and the corresponding value on the variable on the vertical. Line segments that are then drawn connecting the points. A time series plot. Time series plot. So here's your dot plot. Now you have this time series plot. And so you're putting points for each one of those things, and then you're connecting them with lines. So you can sort of see the trends going up, down, steady, have a peak, what caused the peak. So identify the shape of the distribution. If you split a blank distribution down the middle, the right and the left side are blank images. So this is going to be symmetric. If it is a symmetric distribution, so then you're going to have mirror images. Mirror images. So a blank distribution, the frequency of each value of the variable is evenly spread out across the values of the variable. That's going to be a uniform distribution. Let's try this again. A uniform distribution. Now there's another kind of distribution where the highest frequency occurs in the middle and the frequencies tail off to the left and the right. And that's going to be called bell-shaped, a bell-shaped distribution. The graph looks like the profile of you guessed it, bell. That's why it's called bell-shaped, right? So if the longer tail is to the right of the peak, then we're going to say this thing is skewed right. If the longer tail is to the left of the peak, then we're going to say skewed left. So notice uniform, bell-shaped, right? The basic outlines of bell. This, the tail's out here to the right, so guess what? Skewed to the right. This one, the tail's out here to the left, is skewed left. So I hope this helps you with section 2.2 in organizing quantitative data.